Welcome to all in the today's session of Value Added Certificate course, which is being organized by the Department of Chemistry, Pandit NRS Government College, Rohtak. I want to give my sincere thanks to Department of Higher Education, Panchkula, Haryana, for giving the opportunity to the Department of Chemistry to organize such type of programs. It get me immense pleasure to welcome Dr. Suman Lata, Professor and Chairperson, Deenbandhu, Chhotu University of Science and Technology, Murthal, who joined here today in this session as a resource person to deliver an expert talk. He completed his PhD in the area of, their area is very broad. Her main area in the corrosion area, electrochemistry area, many other fields been connected with ma'am. She has presented his research work at national and international level among the research community. She has already guided the large number of PhD scholars who has completed their PhD under the guideship of Dr. Suman Lata, Professor Chairman of DCRUST Murthal. He has undergone through many programs at national and the international level. I also feel proud to extend my hearty welcome to you, ma'am, on behalf of all the participants and our college faculty from our principal side, Major Dinesh Saharan, because we are going to be benefited with your expertise. The theme of the course is such that every branch is directly or indirectly been connected. I would like to mention that our theme is also one of the highest priority of Government of India and remain one of the key challenges to the whole society. I am sure that the inputs and the guidance given by you in this session will go along in enriching our efforts for making meaningful change in the life of peoples. Thank you, ma'am. Thank you so much, ma'am. I welcome again to be a part of this session by accepting our invitation on a very short call, on a very short message, on a very short request. Now I request Dr. Suman Lata ma'am, Professor and Chairperson at DCRUST Murthal, to enlighten us with your precious experience and knowledge. Over to you, ma'am.
So today we will discuss about the topics related to electrochemistry and its importance in our daily life, specifically in material science as well as in biological science and life sciences also. So before starting, let me introduce myself through screen sharing and let me share the screen. Okay, so here it is. Okay. So myself, Suman Lata, Professor and Chairperson, Department of Chemistry at Deenbandhu Chhotu University of Science and Technology, Murthal, Sonipat, Haryana. Here is my email address. If anyone wants to contact with me, then he or she can email on this email address. So now let us start with the essence of electrochemistry and why do we need the electrochemistry and its related topics. So let me go for slideshow. Here it is. So first of all, we will talk about why the electrochemistry is so important, and it also happens sometimes that some students have some kind of phobia regarding the topics of electrochemistry and to learn the electrochemistry topics specifically from the books by foreign authors. But generally, I believe that for electrochemistry, the most important and one of my favorite book is Modern Electrochemistry by Bokris and Reddy. The book has 3 volumes named as Volume 1, that includes basics of the electrochemistry, and thereafter there are 2 parts of Volume 2. One is Volume 2A and another is Volume 2B. So today I will be discussing some important topics from related to the book Volume 2B and Volume 2A, that consists of the concept of electrochemistry, which are, we can say, an essential part of all the materials depending upon the electrochemical phenomena and the electrochemical changes taking place. For example, if we talk about, for example, a battery or a supercapacitor or a solar cell, or we can also talk about the corrosion and corrosion control and the things related to such fields. We need the electrochemistry and electrochemical phenomena at every step. So, first of all, let us talk about the essence of electrochemistry. A special property of the region between a metal electrode in contact with a solution. Obviously, whenever we study about the electrochemical reactions, there is essentiality of a metal electrode placed within a solution and the layer of ions that collide with it in their wandering and stay there a while, because we very well know that we cannot connect with the help of any connecting wire those of the ions diffusing in the electrolyte solution with that of the metal electrode. So therefore, generally the phenomena happens like this, that the layer of ions that collide with the metal electrode in their wandering position, and they may stay there. There means on the surface of the electrode for a while. And during this phenomena, they come across with the transfer of charge. That is, charge transfer takes place when there is a close vicinity of the layer of ions as well as the metal electrode surface. So, this property is the electric field between the electrode and this layer that is formed due to the alignment of ions from the electrolyte side, and through this there is a formation of electrified interface, or we will talk about this electrified interface. Sometimes it is also called as electrical double layer or EDL in short form, or simply we commonly name it as double layer only. So this property is the electric field between the electrode and this layer. It is colossally strong electric field, that is 10 raised to the power 9 volt per meter, but extends only some 0.5 nanometer into the solution side. In other words, we can say that a billion volts per meter is a bigger field strength than one can engineer in a macro device in a laboratory. Therefore, it becomes a special strength of electrochemistry in terms of its essence. So let us go to next slide. Again, why there is need of electrochemical reactions. So as we are talking on the importance or the significance of electrochemistry, so first of all we will talk about the electrochemical reactions. Electrochemical reactions is, I hope, it's a very common thing to know the difference between electrochemical reaction and a chemical reaction. Obviously, the electrochemical reaction contains an extra component, that is transfer of electrons, in addition to the other components as that come across in chemical reactions. So there are some basic differences between electrochemical reactions that make them special in comparison to that of chemical reactions. In junior classes, students are being taught first of all about the chemical reactions, but this is the reverse of the order in which we encounter reactions in our daily life. How? Let me talk about that, how we come across with electrochemical reactions in place of chemical reactions in our daily life. For example, if we talk about digestive processes in the body that are associated with electrochemical reactions rather than chemical reactions on the surfaces of energy converting mitochondrial cells, means to say these mitochondrial cells are sufficient to prepare a metal solution interface. Metal electrode and solution, or in other words electrolyte interface, is formed on the surfaces of these mitochondrial cells. That's why we can say that electrochemical reactions are more commonly acknowledged in our daily life. Another difference is the electrochemical oxidation of glucose, the very basic phenomena of our metabolism. The electrochemical oxidation of glucose coupled to the electrochemical reduction of oxygen as kind of we can say redox phenomena taking place in these cells, means living cells, is part of the process by which our bodies get the electrical charges to work, or our musculature or the energy to power the compressions of the heart pump. Moreover, another very natural phenomena that come across in plants, that is called photosynthesis, that works by means of an electrochemical step as well. In it, water is split photoelectrochemically to produce atomic H, and the H produced later reacts chemically with present in the air to provide food for green plants, which then enter the food chain and give back to us solar energy to power the moving parts of our bodies. Means to say, the phenomena we come across in our daily life are more closer to the electrochemical reactions in place of chemical reactions. Finally, there is a mechanism by which metallic materials gradually break down in moist air, and this process is very common, unstoppable process, but controllable too. That is called corrosion of metals and materials, metallic materials, alloys, etc. So, to conclude the need of electrochemical reactions, we can say that these three great natural processes, conversion of biological energy into muscle power, collection and storage of solar energy in green plants, including grass and trees, and the breakdown of materials, all involve electrochemistry and embrace a significant part of normal life. we can say that purely chemical reactions are less prominent in the natural world. So we will talk about the formation of electrified interface and electrodics again as the essence of electrochemistry. The branch of electrochemistry which deals with quiescent, that is at equilibrium, and active, that is the stage of non-equilibrium, interfaces, the structural and electrical characteristics of the interface, the rates and mechanism of change over from ionic to electronic conduction is called the kinetics of electrochemical reactions, or in a short form it is called electrodics. Now, how this electrified interface is formed? The formation of electrified interface. It occurs in two ways. First of all, if there is no external source of potential to supply the potential to the metal electrode or in any one phase of the system, then what happens? For the formation of an electrified interface, first of all, redistribution of electrolyte particles takes place. Because the electrolyte particles always occur in a diffusion state, moving from one place to another place, therefore, through this phenomena, redistribution of electrolyte particles takes place, with the virtue of which charging electrolyte side of interface happens, that is the charging of the electrolyte side occurs, and that charged electrolyte will induce again a charge on the metal side also, that is on metal solution interface. The metal side will also get charged, then occurs the charge separation, and ultimately development of interfacial potential difference. One more interesting thing here is to tell you that before the formation of electrified interface in the electrolyte bulk, there is always isotropy and homogeneity. As we very well know that isotropy and homogeneity means a very symmetrical system. Isotropic means to say that every property, if we go to any side, any property will not change, it will remain the same, as well as homogeneity. But as far as the electrified interface is formed, the electrified interface and the nearby system becomes anisotropic in nature, as well as it becomes heterogeneous also. Now we are discussing the formation of an electrified interface. First method we have discussed. Now the second method is in those systems in which one of the phases, for example a metal electrode, can be connected to an external source of charge. The formation of an electrified interface can be conceived in the following way. First of all, charge flows from outside source into one phase. For example, the most convenient way is to the metal electrode, and then charging of one phase occurs. That again redistribution of electrolyte particles in the interface due to inductive effect, due to which development of net charge on electrolyte side of the interface. Ultimately, charge separation across the interface, and again the development of potential difference across the interface occurs. In this way, there are two methods to form an electrified interface. Sometimes electrified interface is also named as electrical double layer, or simply EDL is also called and or more simply it is called a double layer. Whenever we talk about any double layer, it directly means to say that we are talking about electrified interface, because interface occurs at every means to say at every boundary. Whenever there are two phases, in between the space is there, that is interface, and if we electrify this interface, it becomes electrified interface. Now, electrical double layer and its essence. Why it is so important, the formation of electrical double layer or electrified interface? Because when charges are separated, a potential difference develops across the interface. And the potential difference, the electrical forces that operate between metal and solution, constitute the electric field across the electrode-electrolyte phase boundary, or in other words, we can say that electrode-electrolyte interfacial region. So it will be seen that although the potential differences across the interface are not large, they come across with approximately 1 volt value, that is not so high. The dimensions of the interfacial region are very small, approximately 0.1, and thus the field strength, that is potential gradient, is enormous, and it becomes of the order of 10 raised to the power 7 volt per centimeter. And the effect of this enormous field at the electrode-electrolyte interface, that can be seen like this. This is electrode and this is solution side, electrolyte side, and this is the interface here, or we can say this is the interfacial region. So the effect of this enormous field at the electrode-electrolyte interface is, in a sense, the essence of electrochemistry. The term electrical double layer, as I have already told, or just double layer, is used to describe the arrangement of charges and oriented dipoles constituting the interface region at the boundary of an electrolyte. So again, the representation of electrified interface, the interface between two dissimilar interfaces, is electrified. Almost all surfaces carry an excess electric charge. Hence, as and when two dissimilar phases come into contact, charge separation occurs in the interfacial region, which results in the generation of an interfacial potential difference, or in other words, we can say that an electric field strength creates there. So this is the representation of electrified interface. Suppose the metal electrode is positively charged, so the opposite charge will be aligned towards the electrolyte side or the solution side, and excess negative charge density occurs there, as well as excess positive charge density towards metal electrode. Actually, what happens at this interface, let me tell in more detail. For example, this is metal electrode, and suppose it is negatively charged. It may have any charge. So, first of all, there is formation of IHP, that is called internal Helmholtz plane. IHP is formed due to the alignment of solvent. For example, we are talking about water as solvent or any electrolyte. For example, NaCl is dissolved in water, then the solvent here is aqueous containing H2O molecules, and these H2O molecules may align themselves like this, as because the water is acting as a dipole here. So this layer, aligned layer, is called HP, that is internal Helmholtz plane, whereas from this solution side or electrolyte side, the positively charged ions in the solvated form will make another alignment like this, where their locus will fall in a straight line, something like this, and this straight line, another straight line parallel to the metal electrode containing positive charge. If we simplify this arrangement like this is metal side and this is solution side. So alignment of these two oppositely charged ions as a double layer, that is called electrified interface or electrical double layer, and it is a most commonly occurring phenomena at every metal solution electrode boundary. Now, what are the applications of electrical double layer or electrified interface? We come across the formation of electrical double layer if we talk about energy storage devices like supercapacitors, battery, etc. in corrosion and its control. Whenever corrosion controlling mechanism is taken into consideration, then there is a formation of electrified interface, as well as in sensors, specifically in electrochemical sensors. We need the formation of electrical double layer in order to look into the mechanism occurring at the electrode electrolyte interface. Now, the types of interfaces. Firstly, we should know that electrified interface can be denoted as an electrical circuit, means its analog as electrical circuit. So if this is the electrode side and this is solution side and this is interface, so this is an analog of a capacitor and a resistor that are being placed in parallel to each other, and it becomes an electrical equivalent circuit for an electrified interface. Now, how many types of interfaces are formed in this way? There are two types of interfaces, that is polarizable and non-polarizable interfaces. If we talk about polarizable interface, means when capacitor and resistor combination is connected to a source of potential difference, if the resistance suppose is very high, then the capacitor charges up to the value of the potential difference, but put out by the source. This is the behavior of a polarizable interface. Means to say, if the resistance is very high, then leakage of current will not take place at this situation, and therefore we can polarize the interface. Whereas for non-polarizable interface, the value of resistance is negligible, approaching to zero, means there is a leakage of charge that can take place, and therefore we cannot polarize this interface. That's why it is called ideally non-polarizable interface. Now comes the concept of image forces. Image forces is a paper parameter and a hypothetical concept, we can say, because whenever a metal electrode, suppose it acts like a mirror and we put a positive charge here, suppose it is kept as at a distance r from the electrode surface towards the solution side or electrolyte side. Now its image will be formed at the same distance, but the image will be virtual like this. So the concept of image forces is that if this original positive charge is having one unit positive charge, that is plus Q, then its image will be having an equal but opposite charge, so that the image forces will always be of attractive nature because of the opposite charges. So they are like the mirror image of charges. They will be equal in magnitude but opposite in sign. Moreover, they are short range forces. Now, we will talk about the various types of potentials and how we can define or we can take these potentials. Now, potential means it is the amount of work done in bringing a unit positive charge from infinity to a point P, a very basic definition of potential. Now, types of potential differences are outer potential difference, surface potential difference, inner potential difference, and electrochemical potential. So, if we talk about outer potential difference, that is represented as M delta S psi. This is the general symbol for metal solution interface as a change. Metal solution interface, and delta represents change. So, outer potential of an electrode, this side outer potential of an electrode, and this side outer potential of solution, that is psi m, and here it is psi s. So the outer potential of the electrode is the work done to bring a unit of positive charge from infinity to a point P just outside the image forces from the electrode. Generally, if I clarify more the concept of image forces, then because I have already told that image forces are short range forces, so we can see that here it is OHP, here it is IHP, solvent dipole layer IHP, that is not shown here, but the fall of image forces, if we move from this direction to this direction, then there will be fall off of image forces. So we can say that the image forces work more prominently only up to OHP level, or we can say OHP layer. So if we talk about outer potential of electrode, that is psi m, means to say that whenever a unit positive charge is taken up to just outside reach of image forces from the electrode, means just outside of OHP. In other words, we can say this. Similarly, for outer potential of solution, again just outside reach of image forces from solution. Suppose this is solution with charge Qs. Now, if we talk about the potential difference, that is outer potential difference, that is represented like this. It becomes the difference of metal outer potential and solution outer potential. The next potential or potential difference, that is called surface potential difference, represented as M delta S pi. So here the work done to take test charge across dipole layer, this is the oriented dipole layer. As I have already told you that suppose water is acting as a solvent for electrolytic solution, then this water acts as a dipole, and therefore there is alignment of these all dipoles. This is uncharged solution, and this is oriented dipole layer. So if any unit positive test charge is taken to the place just crossing this IHP, this is IHP. In other words, this is inner Helmholtz plane or oriented dipole layer. So just we have to make the unit positive charge just to cross this IHP or this solvent oriented dipole layer. In this way, the work done between the metal surface and the solution surface is called as the surface potential difference, that is m delta s chi will be equal to chi m minus chi s. Then comes inner potential difference. Inner potential difference is nothing but the sum of outer potential difference, that is m delta s psi, and surface potential difference m delta s chi, and the symbol for inner potential difference is phi, that is called psi plus chi. This is the potential. And if we talk about the potential difference, inner potential difference becomes outer potential difference plus surface potential difference, that is like this. Now comes the electrochemical potential. Electrochemical potential, that is has a symbol mu bar. It is the sum of chemical potential, this is the chemical part, chemical potential, and ZF phi. Phi again it comes as inner potential. We can put it here ZF psi plus chi also. So electrochemical potential becomes equal to this much. Means that it is the sum of two components. Chemical potential occurs due to thermal motions, and electrical potential, the second half, this part becomes the electrical potential that comes across due to electrical, or we can say the charged forces. So in this way, we discussed about the various potentials as well as the electrified interface and the various potential differences and nature of potential differences, their importance, and the role of electrified interface and electrochemistry in our daily life.
Thank you, ma'am, for giving a wonderful lecture on the basics of fundamental electrochemistry and electrified interface. Because the electrochemistry is very basic need that everywhere in our life, because the potential difference is always been there in every field. आप चाहे कहीं पर भी देख लें, हमारी बॉडी के अंदर देखें, हमारी बॉडी के अंदर जो सिग्नल चलते हैं वो किस वजह से चलते हैं? इलेक्ट्रोड पोटेंशियल की वजह से, पोटेंशियल डिफरेंस की वजह से चलते हैं। करंट का जो फ्लो होता है वो किस वजह से चलता है? पोटेंशियल डिफरेंस की वजह से चलता है। जो बिजली कड़कती है और उसके बाद जो फ्लो होता है चार्ज का, वो किस वजह से होता है? पोटेंशियल डिफरेंस की वजह से होता है। कहीं पर भी देखें, वो पोटेंशियल डिफरेंस की वजह से ही हमारे घरों में जो लाइट जल रही है हर जगह, वो एक जगह लाइट जनरेट होती है, दूसरी जगह आ पाई, किस वजह से? कंटिन्यूअसली फ्लो हो रहा है, किस वजह से? पोटेंशियल डिफरेंस की वजह से। Means everywhere potential difference is required for the flow of the charge, for the flow of the signal, everywhere. So that is very important concept, that is very useful for us. और मैम आपने बड़े ही सहज भाषा में बहुत ही अच्छे तरीके से आपने हमें, हमारे पार्टिसिपेंट को, इस बेसिक ऑफ फंडामेंटल जो आपकी इलेक्ट्रोकेमिस्ट्री है उसके बारे में आपने समझाया, इलेक्ट्रिफाइड इंटरफेस के बारे में हमें जानकारी दी। तो हम बड़े ही डिलाइटेड हैं मैम। तो जब भी हम आपसे रिक्वेस्ट करते हैं कि इन फ्यूचर भी जब हम आपको रिक्वेस्ट करें तो आप हमारे मध्य आए इसी टाइप से और हमें इनलाइट करें आपके नॉलेज से, आपके एक्सपीरियंस से। सो थैंक यू सो मच मैम फॉर कमिंग इन आवर कॉलेज, इन आवर डिपार्टमेंट of Pandit Anaris Government College, Rohtak. Thank you, ma'am.